Hello everyone, welcome back to the channel. So today we are going to cover an important topic in deep learning, that is optimizer. If you have ever trained a neural network, you would wonder that how it actually learns. So this video will gonna tell you about this. Okay, so think of it like a way when your neural network makes a prediction, it makes an error. The error B is being measured by something called as a loss function that we have just covered. Now the backpropagation goes through the network and compute the gradient. Basically it tells us that how much each weight contribute to the error. But here's the thing, backpropagation just compute the gradient. It does not update the weight. That's the job of the optimizer. The optimizer takes those gradient and decide how much do I have to move the weights and in which direction. The core idea is very simple. New weight equals to old weight minus some steps. Every optimizer follow this idea. The difference is just that how you calculate them at each step. Okay, so now talk about some of the basic optimizer. One is the vanilla gradient descent, also called as the batch gradient descent. Now we take the entire dataset and compute the gradient and then updates the weight once. The problem is that if you have million of data, then this is incredibly slow and eats up a ton of memory. So we have stochastic gradient descent (SGD), which updates the weight after every single sample. Super fast per step but very noisy. The sweet spot is mini batch SGD. This is why it is being used in most of the practice. Instead of just the full data set or one sample, we use a small batch, maybe 32 to 256 sample per updates. It's balanced the speed and stabilize really well. But plain SGD has a big problem. It uses the same learning rate for every parameter in every direction. This causes slow convergence and oscillation in the tricky low landscape. Okay, and make it really hard to escape the saddle points. Now we have momentum into the story. Momentum is just like a ball rolling downhill. It accumulates speed in the direction where the gradient is constantly pointing. So instead of zigzagging, your weight moves smoothly towards the minimum. The moment coefficient beta is usually around 0.9. Okay, then we have one more thing, that is the NAG, Nesterov accelerated gradient. This is a smart version of momentum. It look ahead, it compute the gradient where the momentum would take you and not where you are right now. This gives better, more accurate correction. So the section 2 is about adaptive optimization. Okay, adaptive optimizer. So in this we'll be leveling up this. First we'll be gonna go with AdaGrad, also called as adaptive gradient. Okay, so AdaGrad keep and track of sum of square gradient of each parameters. Now this is an important thing, that parameter that receive large gradient get a small effective learning rate and parameter with small gradient get a large one. This is really useful for sparse data like the NLP task. Now here's a problem with AdaGrad, that it accumulate the sum of square gradient keeping growing forever. So eventually the learning rate become practically zero and the learning stops completely. We have one more thing, RMSProp, which fixes this. Instead of accumulating all the past gradient, it uses an exponentially moving averaging, meaning recent gradient matters more than old one. So this stop the learning rate from dying out. RMSProp works really well for the RNN and non-stationary problem. Now the one big problem is ADAM, adaptive movement estimation. This is the default choice for most deep learning task and for good reason. Adam combined best of both of the words, momentum and the RMSProp. It tracks two things. The first, momentum, the mean of the gradients. The second, momentum, the mean of the square gradient like the RMSProp. It is also applied in the bias correction in the early steps because at the starting these estimations are skewed towards zero. The default hyperparameter works really well on out of the box. Beetle of 0.9, Beetle 2 of 0.999, epsilon of 10 to the power of the negative 8 and a learning rate of 0.001. Adam is fast, robust and work across all the architecture. If you don't know which optimizer to use, start with Adam. Here is a modern version for this also, that is AdamW. AdamW is adaptive with decoupled weight decay. Here's the issue with the regular Adam. The L2 regularization get tangled up with the adaptive learning rate, so it does not regularize as effectively as it should be. AdamW fixes this by applying the weight decay directly to the weight, separating from the gradient update. This makes the regularization much cleaner and more effective. If you are training transformer, GPT style models, BERT, VIT, AdamW is one thing you can go with. Okay, so now finally sketching out this all, this section is super practical for you. Let's talk about the learning rate scheduling. A fixed learning rate is almost never optimal. It has too high, your loss will diverge. If it is too low, then the training will take forever. The solution is change the learning rate during training. Here are the solution. Step decay. You simply reduce the learning rate by a factor, say 0.1, every few epochs, simple and effective for the CNN. Second is the cosine annealing. The learning rate follows a smooth cosine curve, gradually decreasing from a max to minimum value. Very popular because it's smooth and doesn't drop too sudden. Third part is warm up. Start with a very small learning rate, ramp it up for the few steps, and then decay it. This is the most important for transformer because jumping in with a large number of learning rate early can destabilize the training. Then we have reduce LR on plateau. This one monitors your validation loss. Okay, the best practice for the transformer, we are going to cover transformer, so then we are going to see that how cosine annealing can be used and how for the CNN we can use the step decay. Okay, that will be going to discuss next. If your loss isn't decreasing, so lower your learning rate, check your gradient and switch to Adam. If your loss is oscillating, then use the learning rate and try a larger batch size. Okay, if your loss function is diverging, then your learning rate is too high, so lower it significantly considering the gradient clipping we have just covered in the previous video. Okay, then we have some of the points about that. If you are stuck at a saddle point, then use the momentum or the Adam. Adaptive methods are much better at escaping the saddle points than a plain SGD. Then, if you are overfitting, then add weights decay. Switch to AdamW to reduce your model size. Alright, so now we are gonna wrap up with completely takeaway about this. So SGD with momentum is still competitive for CNN when well tuned, but it need hyperparameter tuning very carefully. Second, we have Adam that is safely default, but this is adaptive and fast and robust across all the architecture. We have AdamW that is done right for the regularization where regularization matters. We have learning rate that is a single most important hyperparameter. It always include a schedule. We have gradient clipping that is non-negotiable for RNN and a very deep learning network. Then we have adaptive optimizer that converge faster but on smaller image task, well tuned for the SGD on the actual generalization. Okay, so that's all about the complete optimizers in the deep learning. Thank you.